All right, so as we start looking at one-sided limits, the first thing I want to note is some notation that's going to be important to recognize. All right, our notation here for one-sided limits looks similar to our regular limit notation. We have this LIM, and then we have x approaching some number. We're taking the limit of some function f of x. However, we're indicating which way we're approaching it from. Okay? Now, it's pretty easy to remember if you just think of the x-axis. All of the negative numbers are on the left side of the x-axis. So if we're taking the left-hand limit, we're going to put a little minus after the c like that. That's a left-hand limit. Any, not limit. Any left-handers out there? Anybody left-handed? No? Wow. I'm left-handed, but wow, both classes, not a single left-hander. We're defying the statistics here. Yeah. So, all right. So there's our left-handed limit. Our right-hand limit. How do you think that looks? Better.
Same thing with a plus instead.
Yeah, same thing with the plus sign, okay? Same thing with the plus sign. All right, that is our right-hand limit. Okay? So we have our left-hand limit, our right-hand limit. Now, let's look at how this can be used and what we're talking about when we're talking about a left-hand limit and a right-hand limit. You'll notice here in this example, we have the limit as x approaches 0 from the right of that reciprocal function 1 over x. Okay? So we are approaching 0, but we're approaching just from the right-hand side. Okay? Now, what is this function doing as we come from the right-hand side towards 0? It's increasing to where? To infinity, okay? So this is approaching positive infinity. And remember, for our class, what are we going to say then about the limit? The limit does not exist, okay? The value of the function approaches positive infinity, so therefore the limit does not exist. Now, here's one that actually does exist. Does anyone know what this would look like? The square root of 4 minus x squared? Wait, what?
Like this.
Okay, it's going to look like this. It's going to be half a circle, right? If we had negative square root of 4 minus x squared, we'd get the bottom half of the circle. Okay, so this is the top half of the circle that has a radius of 2. Okay, a radius of 2. So let's actually draw this. So there is our function f of x. Okay? Now, we want to find the limit as x approaches negative 2 from the right. So let's write out our notation for what we're talking about here. It's the limit of 4 minus x squared as x approaches 2 from the right. So we have a little plus sign there. Okay? Or sorry, negative 2. Negative 2, thanks. Lost my negative. Okay? So here's our negative 2, and I'm approaching negative 2 from the right-hand side. Okay? So what's the value of our function approaching as we approach negative 2? 0, okay? 0. So we would then say the limit from the right is 0. What would I say about the limit as x approaches negative 2? Why do you say that one? You guess. Well, let's think about it. In order for a limit to exist, what has to happen? There's 3 things. Left has to exist, right has to exist, and they have to be equal, right? We just showed that the right-hand one exists, and it equals 0. What's the left-hand limit? It's not there. There's no function over here, right? The function doesn't exist over here. It's not defined. Therefore, there is no left-hand limit. So we would say the limit as x approaches negative 2 does not exist. But we are able to look at the limit as x approaches negative 2 from the right. This is where these one-sided limits can be helpful. Okay? Or one of the places where they could be helpful. Okay? Let's take a look at another one here. This is kind of an interesting function here. This notation. This is the greatest integer function. It's the greatest integer such that n is less than or equal to x. Okay? Sometimes we'll call this a step function. Alright, and I'll show you how to do this on your calculator as well. Okay? So if I were to sketch this, I'm going to go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? So what this would look like is this. It's less than or equal to the value. So x is less than or equal to 0. X is less than or equal to negative 1. X is less than or equal to negative 2. Okay? Here, x is less than or equal to positive 1. X is less than or equal to positive 2. Whoops, went a little far there. And here's positive 3. Okay? So there's that graph. Now, if you wanted to graph this on your calculator, okay, on the calculator, you would go to Math, Number, wait, where'd it go? Oh, I looked right at it. Math, number, and then number 5 is integer, okay? So on the calc, alright, hit the math button, hit the right arrow so that you're looking at number, and then number 5 is int. Okay? That's the greatest integer function. Okay? So that'll be on the calculator. It'll look kind of like what I just drew. The thing with the calculator though is it doesn't show you the closed points and open points. It just has little lines. Okay? Yes? Inspire, you could actually just type in int with the QWERTY board on the bottom. Alright, so here's part 2. The limit as x approaches 0 from the left. The limit as x approaches 0 from the left of this greatest integer function. By the way, we often use this like double bracket here to indicate that. What is it? As we approach from the left-hand side, what's the limit as x approaches 0?
I have a question, like, not the answer. What is that graph, like, what exactly did we just graph?
It's the greatest integer n such that n is less than or equal to x. So, if x is 1, then the greatest integer would be 1. But if x is 1.2, it's the next greatest integer. That's why it jumps up to the next integer.
Okay,
And that's why they call this like the step function.
okay, thank you.
It's kind of like if you were, I don't know, if you were buying bags of stuff to make something.
Right, like you can't.
You can't buy a
you can't
fraction
have
of a
2.5
bag.
Kids, you would have, like one of those things.
Yeah, you can't have a fraction, or you can't, like, if I'm buying chocolate chips to make cookies or something, and I need 3 cups, but one bag only has 2 cups in it, I've got to buy a second bag. I can't just go in and buy half of a bag. You know, so my cost goes up, whatever the price is per bag. Even if I only need just a tiny bit of that next bag, I got to buy a whole nother bag. You know, that's kind of the idea there. Or what this type of a function might be used for. Okay?
Thank you, that was helpful.
Good. Alright, so what is it approaching as we approach 0 from the left?
How about -12? Oh man.
No. Look, as we're approaching 0, here's 0. As we approach from the left, what is our function approaching? 0. Okay? Right here. There we're approaching 0 from the left. Does that make sense? Okay? So we would say that the limit there is 0. Now, the limit as x approaches 0 from the right okay. Who said that? Yeah. It's 1, that's right, Terry. Okay. As we approach from the right, we're approaching 0 from the right, it's approaching 1. Even though it doesn't equal that at 0, it's approaching 1 as x approaches 0. Okay, so here you have a different left-hand and right-hand limit. Okay? So there's another example there of a case where we can use this. All right.
The restriction, so when we put that in the calculator, we put integer, and then what do we put inside of it?
Inside the parentheses, just put x.
Oh, okay.
In this case, it was the greatest integer x.
Oh, okay.
You can add other things in there like 5x or something like that, but in this case, it's just x. Okay. All right. Let's look at a couple of other things here. Want to look at a concept called continuity, and we're also using this idea, the left and right hand limits, and our rule for when a limit exists. Okay? The left and right hand limits have to exist and they have to be equal. Okay, so we're going to find 3 things here for each of these. It may be a little bit tough to see here, but this is the limit as x approaches c from the right. Then we're going to find the limit as x approaches c from the left. And then we're going to use those 2 answers to find out finally what the limit as x approaches c is. Okay? So we can even make ourselves a little table here. X approaching c from the right. x approaching c from the left, and then x approaching c, and then it says discuss the continuity. Basically, when they're saying discuss the continuity, we're simply asking, is it continuous at that value that we're looking at, okay? In our case, we're looking at the value c equals -2. So it's the limit as x approaches -2 from the left, from the right, and together. Okay. So we'll make ourselves this table. Okay, so for this first one here, number 2 on here, as x is approaching -2 from the left-hand side, what is our function approaching? It's approaching -2, yeah. Okay, so that's -2. How about as we approach from the right-hand side? It's -2. Okay? Hang on one second here. I was doing this the other day too. Okay? So, from the right-hand side, -2. From the left-hand side, -2. So what's the limit as x approaches -2? It's -2. Okay? Because those are equal. And also because we would say that this function is what around -2? It is continuous. Okay? So yes, it is continuous around -2. Okay? How about this next one here? Here we have what looks like some kind of an absolute value function, but then it has this one displaced point here at -2, 3. Okay? But again, we're going to approach c equals -2. So as we approach from the left, what is the value of our function approaching? It's approaching 2. Okay. As we approach from the right, it's approaching 2. So, since it hits the point -2, 3, what's the limit as x approaches -2? Well, we have a debate now. 2 or 3?
3 for sure.
How many of you say 2? Okay, how many of you say 3? Okay, how many of you aren't really with us? Couple. All right, you'll catch up. All right. So, remember, what's the key word when we're talking about limits? Approach. All right. What is this approaching from both sides? 2. Does it equal 2? No, it actually equals 3. But it's approaching 2. So the limit equals 2. Alright? The limit equals 2 here. Okay? Now, is this continuous? No. But notice here, the limit does exist because while it was not continuous, there was just a hole there, right? If there were an asymptote and this was going off to infinity, there would not be a limit. Okay? But there's a hole, and that's why the limit still does exist. Okay? Now, 6 is a little bit different. Okay? As we approach, in this case we're approaching -1. Here, notice c is -1 in this case. As we approach -1, what is our function approaching from the left? It's approaching 2. as we approach -1 from the right, what's our value of our function approaching? 0. So what does our limit equal? It does not exist. Okay? It does not exist. Both side limits do exist, but they're not equal. Therefore, the limit does not exist. Okay? So, is this continuous? Obviously not. There's this big jump. Okay? It jumps from near 2 down to 0. Now, you don't have to write all of that, but you need to recognize, no, there's no, the limit does not exist here because there's an actual jump. We're approaching two different values from either side. Okay? All right. Were there any questions on any of these before we move on? By the way, in some of the homework, it says discuss continuity. We're really just trying to determine, is it continuous around there or not? Okay? A little later here, we're going to talk about being continuous on an open interval as opposed to being continuous on the closed interval. And that's something that we'll, like I said, we'll look at here in a minute. But let's take a look at this one real quick here. Here we have two other functions. Do you guys know what that would look like on A? The limit as x approaches 2 from the right of that function. What was that function going to look like? Yeah, it looks something like that, William. That's right. Okay, we've got, if I didn't have the absolute value, what would this thing equal?
1.
It would equal 1, right? There would be a hole at 2, but it would just equal 1 all the time. So you'd have this horizontal line, okay, at 1. Now, when x is greater than 2, that is exactly what happens. But what if x equals something smaller than 2? What do we end up with? Try it. Pick a number in your head that's smaller than 2. Plug it in. What do you get?
Keep one place that's at the opposite of the x-axis, under the like symmetry.
Okay. It's reflected.
Yeah,
So
that's
it's
reflected.
Okay. Yeah, it's reflected down across the x-axis. I think someone said it. -1. Okay. It's reflected down here, and that's because this, the absolute value, always stays positive. So even if we had 1 minus 2 is -1, now it's made positive by the absolute value. But the denominator, 1 minus 2, is -1. So it's now 1 over -1. Okay? So we have this reflection here, but it's going the opposite direction here. So everywhere below 2 is -1. Okay? Okay? So, as x approaches 2 from the right-hand side, what is our function approaching? 1. Okay? It's approaching 1. Now guys, think about this here. Notice on a lot of these, getting the actual limit's the easy part. The challenging part is recognizing and graphing the function, okay? That's why in pre-cal honors we spent so much time working with graphing functions and stuff, is because that's going to be an important thing to be able to do here. Sketching different types of functions, even like on B, a piecewise function, and then being able to draw stuff out of that, okay? Now I'm going to pause this here for a second. I want you guys to try to sketch B on your own and find that limit there as x approaches 1 from the right. Alright, you guys are doing pretty well getting this eventually. These piecewise ones are a little strange sometimes to work through, okay? Oop, wrong button. Alright, so that's about what that should look like, okay? One thing that may help you as you're graphing piecewise functions, I find this helpful for me sometimes, maybe not with a line like this, might be a little simpler, but if it helps you to go ahead and like sketch the entire thing, but maybe make it dotted first, and then only make solid the part that's actually part of the function. Some people like to do that. Like here's this first part, that's just the line y equals x, right? So that's this right here. But it only goes up to where x is 1. So I'll put an endpoint here and only make this left-hand side solid. Okay? If that helps you sketch these, go ahead and do that. I don't mind if you have some extra dotted line parts showing, as long as you make it clear what the graph you're working with is. Okay? Now, what did you guys get for the limit as x approaches 1 from the right? 0, okay? This is 0. As we're approaching 1 from the right, we're approaching that value of 0. Okay? Okay. So we've been talking about these left-handed and right-handed limits. I want to revisit that concept that we talked about a few times already and just kind of readdress it more formally here. In order for a limit to exist, we said the left and right-hand limits have to exist and be equal. Okay? So here's kind of the formal theorem that states that. Let f be a function and let c and L be real numbers. The limit of f of x as x approaches c is L if and only if. And then you have these, and it's a little hard because it didn't come through all the way on the PDF here. The limit as x approaches c from the left of f of x is L, and the limit as x approaches c from the right of f of x is L. Got to approach the same number from both sides. Same thing we've been saying, just here's the formal theorem now that we know the concept of left and right hand limits. Okay? Now, one application of these limits is to determine whether there is continuity on a closed interval. Now, what's the difference between an open interval and a closed interval? Someone help us out here. What's the difference between an open interval and a closed interval?
What does it closed mean? It is equal to that point, and then open it's like it doesn't equal it, it approaches it.
Okay, good. The open just approaches those end values but never equals them. The closed interval, notice here, indicated by these square brackets, shows that A and B are part of the interval. Those values are. The parentheses here means that it's just going to A and B, or approaching A and B. Okay? So, let's look at what this is saying, alright? A function is continuous on the closed interval AB if it's continuous, first of all, on the open interval. In other words, there's nowhere in the middle of this interval that has a hole or an asymptote or anything like that. Okay? But here's the key, and here's where the left and right hand limits come in. Okay? The limit as x approaches a from the right of f of x equals f of a. Alright, so notice here, this value right here is f of a. Okay? As we approach a from the right, we're approaching this value f of a. Okay? Therefore, we would say that it is continuous from the right at a. That's what this right here is saying. Okay? Oh, my pencil's dying on me. So it's continuous from the right at A. Now, look at the second part of this. The limit as x approaches b from the left of f of x is f of b. Alright, so here we have this value, f of b, and as our function approaches b from the left-hand side, we are approaching f of b. Okay, we're approaching the value of the function. And basically, you remember the one we just looked at earlier where it looked like the absolute value function, but there was a hole and then that random point up higher? Okay? That's what we're trying to avoid here, is a situation where, hey, the function's approaching a value, but it's not really defined at that value, it's something else there. There's some kind of a jump in the graph. That would make it not be continuous on the closed interval. Here, it's continuous from the right at A, and it's continuous from the left at B. So therefore, we would say that here, f is continuous on the closed interval AB. Okay? Because it's continuous from the left at the one endpoint, it's continuous from the right at the other endpoint, and it's continuous in the middle. Okay? Alright, so an example here. An example we can work through here is f of x is the square root of 1 minus x squared. Again, another semicircle. Okay, here the semicircle has a radius of 1. So we want to determine what the continuity of this function is. Okay? We can see that it's continuous in the middle. Alright? We could even kind of color code this here. Here it's continuous in the middle. So first of all, it's continuous on the open interval AB. Or I should say, instead of AB, we have numbers now. -1 and +1. Okay? So, let's look at the left side of this interval, -1. Okay? What is f of -1? 0. Yeah. Square root of 1 minus -1 squared is 0. Okay? as I take the limit of f of x as x approaches -1, what is this function approaching? 0. Okay? Therefore, it's continuous from the right at -1. Okay? So it's continuous from the right at -1. Okay? And I know it may be tricky because you're looking at the left side of the interval, it's continuous from the right. But you're coming from the right towards the left. That's why.
This is all for example 6.
This is all for example 6, yes. Okay. And then, thirdly, let's look at the right-hand side. What is f of +1? Yeah, it's 0. And what's the limit of f of x as x approaches +1? It's also 0. Yeah, you see it's approaching 0 here. So therefore we would say it's continuous from the left at x equals +1. Okay? Now I know this is maybe a lot of writing, or it may seem a little bit tedious writing here, but this is the kind of thing that, you know, is kind of part of this course. It's getting into some of the more technical aspects of what's going on mathematically here. Okay? So we're looking at this continuity on the closed interval. Now that we have actually proven this, we can now state, based on all of this, therefore, f of x is continuous on the closed interval -1 to 1. Okay? Again, this is one difference kind of between AP and IB stuff, is that AP often will prescribe a particular way you have to do certain problems. If you're told to show that this is continuous over the closed interval, you should show all three of these aspects. Stating it is continuous on the open interval, showing that it's continuous on one side as you approach from the right, and then continuous on the right side as you approach from the left. And then you can say it's continuous over the closed interval. Okay? IB kind of gives you freedom with a lot. They don't get this technical anyways, but they give you a lot of freedom on, as long as you get there, it doesn't really matter how. Just get there and show your work and show a logical thought process, and it's okay. AP is a little bit more prescriptive sometimes in how they want you to do things. So let's sum all this up by looking at some properties of continuity. A number of these things we've kind of observed already, but I want to state here and make a couple of observations, and then we'll see how we can actually use this. Okay? So some properties of continuity. It sets the stage here for us. B is a real number. F and G are continuous at x equals c. Then these are also continuous. Okay? So, a scalar multiple. If you know a function is continuous, then any multiple of that function is still going to be continuous. That's what that's saying. The sum and difference. if I have a continuous function plus another continuous function, I'm going to have a continuous function as the result. The same thing applies with multiplication. Okay? The same thing applies with division as long as the denominator doesn't equal 0, because then you have a problem. Okay? But as long as that denominator doesn't equal 0, you can determine, hey, continuous divided by continuous will give me continuous. Okay? So, let's consider some different options that are continuous at every point in their domains. That's an important phrase there. In their domains. Remember all that practice you did in Algebra 2 and pre-calculus on identifying domains and ranges? Okay? Here's where that pays off a little bit. Okay? You have to look at points in the domains. What's the domain of a polynomial function? Any polynomial function. All real numbers. So guess what? Polynomial functions are continuous over all real numbers. Okay? A rational function, except for the points where the denominator equals 0, that rational function is always going to be continuous. Okay? The radical functions, okay? Again, except for the values that make an even index radical negative and give you complex numbers, it will be continuous. Alright? And then finally your trig functions. You guys know sine, cosine. Those are defined for all real numbers, so they're always continuous. Tangent and cotangent and secant and cosecant, those have asymptotes. If you don't remember where the asymptotes are, that's where looking back at your unit circle is helpful. Okay? You know tangent, sine divided by cosine. So where is sine 0? That's where tangent's going to be 0. Where is cosine 0? That's where you're going to have the asymptotes. Because you're going to have sine divided by 0. Alright, so that's how you can help remember your domains for these functions. Alright, so guess what? Putting this together with this, then, x plus sine, x is continuous for all real numbers, sine is continuous for all real numbers, so x plus sine is continuous for all real numbers. Okay? 3 times tangent. Tangent is defined so long as x does not equal pi over 2 plus pi n, where n is an integer. Okay? Those are all the asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. So as long as it's not that, then that function's going to be continuous. And here, so long as cosine does not equal 0, this will be continuous. So think where cosine is 0. It's at pi over 2, 3 pi over 2. Same thing actually as tangent. Okay? So, one last theorem here and then we'll test a little bit with a couple final examples. Okay? If G is continuous at some number C, and F is continuous at G of C, then the composite function given by F of G of X is continuous at C. Okay? So notice here, F does not have to be continuous at C. F has to be continuous at G of C. Alright? So if I were, looking at, say, tangent of the sine of x, and I was looking at x equals pi over 2, okay? Well, sine of pi over 2 equals what? 1. So, is tangent continuous at 1? Yeah. Okay. 1 is somewhere in there between 0 and pi over 2. Okay, it's somewhere in there, so it's continuous. So, since sine is continuous at pi over 2, and tangent is continuous at sine of pi over 2, which is 1, then tangent of sine of x is continuous at pi over 2. Okay? So that's how that can work. Even though we all know tangent of pi over 2 is undefined. But that doesn't matter here. Okay? Okay. So, let's talk about these down here. We actually already mentioned this one here. F of x is tangent. It's continuous. It's continuous as long as x is not on any of the asymptotes. So how could we write an interval showing that? X cannot equal pi over 2 or pi over 2 plus any multiple of pi. We could say where n is an element of the integers. That z with kind of the double cross line is the integer symbol. Okay. How would I write this as an interval? Here, I'll get you started. Parentheses, the comma in the middle.
That's how we know.
Okay. Well, let's start with one interval. Give me an interval where it would be continuous.
What?
Well, that's a value. What's one interval? A range of numbers.
1 to 10.
Pi over 2, pi over 2.
0.
Okay. From pi over 2 to 3 pi over 2. That would work. Okay. So pi over 2 to 3 pi over 2.
But did we just make up numbers? Like up here?
Well, we just made one up for this, but we actually can generalize this to cover all of them. Okay?
Yes.
Because it's not just this one, but it's also, remember tangent looks like this? And you've got these asymptotes in the middle. It roughly looks like that, okay? Each of these pieces is an interval where it's continuous. So let's say this one is the pi over 2 to 3 pi over 2. What would this one be? Yeah, negative pi over 2 to pi over 2. And we could even do another one, negative 3 pi over 2 to negative pi over 2, and so on. So, let's actually use that one that's kind of centered on the origin here. Well, let me erase. Let's do that. Okay. If I go negative pi over 2 to pi over 2, but then each time I need to change it by pi. That's a way of generalizing it to give me all of the different intervals where tangent is continuous. Okay? Any questions about that? Does that make sense? Okay. Alright, let me get rid of this a little bit. I don't know why I can't make this bigger. It's as big as it gets. Okay. Okay, alright, we'll have to do the other two later at some point maybe, but that'll be good for today.